we have learnt that energy density in a magnetic field B is given as 1 over 2 mu 0 B square. Let us now use this to see some examples. So, example 1, I will take a long solenoid that has n turns per unit length. So, it is carrying current I and it has n turns per unit length, and it is carrying current I, so that there is a magnetic field established here B. Then the energy is going to be 1 over 2 mu 0 B square. This is the energy density. B in a solenoid, I know what it is. So, it is going to be 1 over 2 mu 0. B is mu 0 and I square. Therefore, the energy density is given as mu 0 n square I square divided by 2. Let us see if this makes sense. Per unit length energy stored, therefore, is going to be the area of cross section, let us call it A, times the unit length. So, that is going to be the volume. So, energy stored per unit length is going to be area of cross section A mu 0 n square I square divided by 2, and this should be equal to. So, energy stored per unit length is mu 0 n square I square divided by 2 times A. This should be equal to 1/2 L I square, and this gives L is equal to A mu 0 n square. This is the inductance per unit length. This makes sense. For a solenoid in per unit length, the inductance will be phi total flux, that is passing through all these n turns divided by I, which is going to be n times the area for these n turns. The field is n mu 0 I divided by I, which is A mu 0 n square. So, these two match. So, that is one example where we have seen how the energy calculated by the energy density of B is same as it matches with the inductance through the inductance method. Should not surprise you, because after all we derived that formula starting from an inductance formula. Next example, I will take a current carrying wire enclosed in a shell through which the current comes back. To save myself from mathematical difficulties, right now I will take this wire to be such that it has a radius A and is hollow, so that the current flows only on the surface of the wire. So, current is flowing only on the surface, inside there is nothing. So, this radius is A and let the outer radius be B. By Ampere's law, B in this wire is going to be mu 0 over 2 pi r times I, and this B, if the current is going up, B field is circular like this. And therefore, the energy stored, since B is 0 inside, this hollow, B is only in this region. So, the energy stored, energy density is going to be 1 over 2 mu 0 times b square mu 0 square I square over 4 pi square r square, which is equal to mu 0 over 8 pi square r square I square. If I were to calculate energy stored per unit length, so energy stored per unit length, this will be equal to mu 0 is a constant I square over 8 pi square integral a to b 2 pi r dr divided by r square, and this comes out to be mu 0 I square over 4 pi log of b over a. This by definition should be equal to 1/2 Li square. So, 1/2 Li square is equal to mu 0 I square over 4 pi log of b over a. I square cancels and I get L equals mu 0 over 2 pi log of b over a. Let us see if this makes sense. Again, in this wire which is carrying current I, and outside the current is coming back, the flux per unit length will be in this area which I am showing by this shaded region, and this is going to be B times dr times unit length. Dr is this and unit length is this way. This will be the flux r varying from A to B, which is equal to mu 0 over 2 pi I integral dr over r A to B, which gives me mu 0 over 2 pi log of b over a times I, and it should be equal to Li, and therefore, this gives me L equals mu 0 over 2 pi log of b over a. The two match. You may be wondering how come I am calculating energy from that I am getting an inductance and then trying to match them. Next example will show the importance of that. In the next example, I take what is known as the distributed current. And what we will do in this is, we will take a wire which is solid and it is carrying current I, and the current comes back through an outer casing which is matching exactly the same radius as the wire. So, it is through this outer casing that the current comes back. Let us calculate the magnetic field inside this wire and the energy stored in that, assuming that the current is distributed over the entire wire evenly. Let this radius be A. Then by Ampere's law, if I were to calculate the magnetic field at a distance r from the axis of the wire, we are going to have B times 2 pi r is equal to mu 0. Total current is I, which is distributed over pi a square, and therefore, current enclosed will be I over pi a square times pi r square. Let us cancel this pi, and therefore, I get B to be mu 0 over 2 pi a square times r. So, the field inside the wire is increasing linearly up to A, and then it becomes 0, because for outside the net current enclosed is 0, and therefore, the energy stored, energy per unit volume, is going to be equal to 1 over 2 mu 0 times mu 0 square r square over 4 pi square a raised to 4, which is equal to mu 0 over 8 pi square a raised to 4 r square. Let us now calculate the energy stored per unit length, and that is going to be mu 0 over 8 pi square a raised to 4 r square times 2 pi r dr integrated over r going from 0 to the radius a. Let us calculate this, and this comes out to be, so we are calculating energy which is equal to integration 0 to a mu 0 over 8 pi square a raised to 4 times 2 pi, there is r 2 pi r square 2 pi r dr, which is equal to, this 2 pi cancels here and gives me 4 pi. So, this comes out to be mu 0 over 4 pi a raised to 4 times a raised to 4 divided by 4, which is mu 0, a raised to 4 again cancels, over 16 pi, and I had forgotten one, I square, and this should be equal to 1/2 L I square. These together then give me that L should be equal to mu 0 over 8 pi per unit length. What if I calculate L through the flux formula? That is, I calculate the total flux divided by I. Let us see what answer do we get. The answer I am going to get in that case is, let us take this wire in which magnetic field lines are going around, and B we have already calculated in the phi direction, which is equal to mu 0 over 2 pi a square I times r. So, if I were to calculate flux per unit length, I will take this area of thickness dr and calculate. So, flux is going to be B I over 2 pi a square r times dr 0 to a, which gives me B I over 4 pi a square times a square cancels, and I get, where is B? Sorry, this B is not B, it is mu 0, it is mu 0. So, this gives me mu 0 over 4 pi I, and if I equate this to L I, I get L equals mu 0 over 4 pi. Which answer is correct? Earlier answer is mu 0 over 8 pi, this time I am getting mu 0 over 4 pi. So, in the cases where there is a distribution of current, you will get two different answers through the energy method or through flux by I. This actually answer is not correct, because in this case what is happening is that the current is distributed, and therefore, the flux is due to many different currents, and one has to use something called the flux linkage method, in which you take flux due to each small current, multiply that by I, sum it over, and then get the answer. But it is safer to use than the energy method, where B at any point is given due to all the currents, and the answer you get is correct.